All right, the recording is started. So today's lecture is going to be a little bit on the abstract and mathematical side, and your lab follows the lecture content quite closely. So that means, if you're not understanding a concept, you probably want me to clarify as much as I can, or to use example to illustrate, some of the concepts. Taking notes would be helpful, okay, especially when we get to the actual two's complement discussion. But we'll start with some math stuff first, just so that we understand, why two's complement works. All right. So up to this point, we have talked about base conversion, and just to illustrate or just to remind you guys what base conversion is about. So I'm going to start with a binary representation and then convert it back into the value that it is representing. So I'm going to pick, a particular bit pattern that is already in the notes, okay? We'll pick 1101. So 1101 as a base 2 number, what value is it representing? So that's the question. Sorry? Oh, you're trying to figure it out. Okay. So a number is essentially an alias, okay? Is a name for a particular value. So the question is, this is a name, but what value is it representing? 13, that is correct, okay? Because it has to do with this one here, is representing the number of ones. This is representing the number of twos. This is representing the number of fours. This is representing the number of eights. So we have 1 8, 1 4, and 1 1. And when you add up 8, 4, 1, you get 13. So this is 13 as a value in base 10. Okay, so that is all cool. So now the question is, how do we represent negative values? The answer is based on the base conversion, equations. You cannot. Why can't we represent negative values? Because the sigma looks like this. You should not have to write this down because it's actually in my notes. I'm just going to write it here anyway. Okay? So it's a sigma notation where I is an integer. It goes from negative infinity to positive infinity. D of I is representing digit I, and that is being used to multiply b to the power of I, where b is the base. Do you see anything that can be negative? Nope, the digit cannot be negative. The base can be negative, but then really odd things will start to happen, so we don't use negative bases. So b is non-negative, d of I is non-negative. I can be negative, but it still doesn't make the sigma negative. Okay, there's no way for this sigma to be negative. So that would be a limitation if this is the only way we store values in a computer in base 2, it becomes a problem because we cannot represent negative values. So why do you think negative values are important? Well, so we can represent the national debt. It's a huge negative number, okay? Fortunately, 64-bit can also represent, really a lot of numbers, so we are not going to run out of digits in base 2 for a while. Knock on wood. Anyway, so now today's lecture is about how do we represent negative values when all we have are zeros and ones. There are no signs, okay? Because the first thing people think about is, why don't we just add a sign to that number and then we are done with it? The problem with that is then you have to redesign the adder and the subtractor. Okay, we cannot reuse the circuit, that we didn't really kind of work on the circuit in this class, but we kind of speculate that a circuit can exist to perform addition and subtraction because we already talked about the B and the C. We talked about how the XY can determine the Q, and also the K for addition, the T for the subtraction, and all the other bits. So what we'll do today is we are going to first talk about fixed width. Okay, so that means when you talk about an integer in a computer, it is always having a fixed width, which means it is a fixed number of digits. So typically we go by um, hmm, let me see how I can put it this way. It is 8 times a power of 2. Okay, what does that mean? That means 8 times 2 to the power of 1, 2 to the power of 0 is just 8. 8-bit wide, an 8-bit wide representation is typically called a byte, B-Y-T-E. If you double that, you get 16-bit, which is 8 times 2 to the power of 1. Okay, with a 16-bit number, we can represent roughly from negative 32,000 to positive 32,000, which is okay, but it's not really that big of a range. And then the next one up is 32-bit, which is 8 times 4, and 4 is 2 to the power of 2. So that will give us negative 2 billion to positive 2 billion. Okay. If you look at 2 billion, at the day, when, let's say 40, 50 years ago, a billion is a pretty big number. Okay. Most people, most companies are not worth $2 billion. Okay. IBM was not worth $2 billion back in those days. And these days, how many billionaires do we have just in the Bay Area? Okay. That's my point. Okay. And that's why you're in this class, right? You want to be the next billionaire. Um, so the next one up is 64-bit, okay, which is the current standard. So 64 is 8 times 8, and 8 itself is 2 to the power of 3. So that's why I said earlier the width or the bit width of a number in a computer is 8 times 2, 8 times a power of 2, because 2 to the power of 0 is 1, 2 to the power of 1 is 2, and so on. And that's why, I said, I extracted the structure earlier. So is that part understood? The bit width of a what we call a word inside the computer, which is the integer width, is fixed, and it is typically 8, 16, 32, or 64. Now, if you ask me, are there 128-bit integers? Yes, they're uncommon, but you can make 128-bit integers just fine. No, no problem. So the first question or the first thing we need to understand is the range. So um, if W is the width of a number, then the unsigned value can go from 0 to 2 to the power of W minus 1. Okay, so is that understood? Does everybody understand what this is representing? If you use this summation here and you have a fixed width integer, which means the I really just go from 0 to 8 to 7 to 15 and so on, because remember, we are stopping at W minus 1, because digit 0 is taking one digit already. So the digit where we stop is W minus 1. So let's double check this number here, okay, just to make sure it makes sense. Let's just say W is 4, okay? So on the whiteboard, I'm writing down W is 4. The question is, what is the largest value you can represent using only 4 binary digits, which is what we call a bit? So, well, you can enumerate 0, 1, blah blah blah, all the way to 1111. So the question is, what is 1111? Well, we know 0 is just 0. 0, 0, 0, 0 is 0. What is 1111? No, 15. That is correct. So 1111 in base 2 is 15 in decimal, because it's 8 plus 4 plus 2 plus 1. So are we doing okay so far? Now, if you cannot look at 1111 in base 2 and in your head compute it is 15, it's okay. Okay, that part I'm not expecting. On the other hand, I am expecting you to understand, why 1111 is 15, or how to calculate that it is 15. It might take you 30 seconds or a minute to kind of go through the arithmetics, but you should understand how to do it. If you do not, that means you still need to study a little bit more of the previous material, okay? Because all of that stuff, they're all connected. It is really important. Okay, So now we plug that in, okay? What is 2 to the power of 4? Because W is 4. 2 to the power of 4 is 16. 16 minus 1 is 15. Okay, I think that works out. Okay, so it is always important, when you look at something that is quote unquote abstract like this, to plug in a concrete value. And obviously, I did not read ahead of myself because I was using exactly that example on the next paragraph. Are we good so far? Okay, so reading the material ahead of time is also important. It so now the question is, only using 4 bits, how is 19 represented? So this is an interesting question, okay? It's an interesting question because there are two possible answers. You can say it's not possible, okay? It is out of range, it is not possible. Or you can say, maybe I can look at equality a little bit differently and then say that 19 is sort of representable using 4 bits. Okay, so that's basically what the next paragraph is going to talk about. It is called congruency. So it's a mathematical concept. Okay, so we are going to talk about this mathematical concept, which is called congruent modulo something. So in this case, there are several representations. So these 3 bullet points, the first two are about representation. The last one is the actual definition of the notation of the previous 2 points. Okay. In other words, you look at the first bullet point, it is basically saying, if A and B are congruent modulo n, this is how we write it. It's just a representation. Is that okay? Just a syntax of some obscure concept that I have not explained yet. The second one is my representation. It's just a lazier representation. So we can say A and B are congruent modulo n. I just do not want, I just don't like to write mod n in parentheses. That's all. Is that okay? So the third bullet point, which is this one here, is explaining the actual concept of what does it mean when we say A and B are congruent modulo n. Are we good so far? Okay. All right. So let's double check that we understand every single symbol on the third bullet point. Okay. I think we all understand equality in the case of integers. Okay. Are we good so far with just equality, plain equality? We good? Okay. Are we good with addition? This is plain old addition, okay? It's not an or, it's just a addition. What about multiplication? We good with multiplication? And by the way, v has to be non-negative as an integer. A can be positive or negative as an integer. Ka and kb can also be just any integer, can be 0 as well. And then n has to be non-zero. Okay, so those are the restrictions. It has to be non-zero and also non-negative. All right. This little symbol here, what does it mean? It means and, it means conjunction, or in C++, it is the same thing as ampersand, ampersand, okay? So I'm just using the mathematical symbol for and over here. So once again, we have some constraints here. Ka, kb can be just any integer, has no restrictions. V has to be at least 0, but it cannot it has to be at least 0, but meaning it cannot be negative. And n has to be an integer that is at least 2 because it is usually corresponding to a base. Okay, so are we okay with all the restrictions on a, b, v, ka, kb, and n? Are we good? Okay. So now we are going to work out an example, okay? So the example that I have included, is 3 and 19. So let's go ahead and check out some of the other examples. And right away, I'm going to start with something that is in the later part of the module, but I'm going to talk about it now. So we'll go ahead and take a look at -3. Okay, this is A, and then B is 13. Okay. So plug in A being -3 over here, plug in B being 13 over here. Is that okay? So now we set up two equations. We want to see if we can express -3 as some kind of equation, and we'll just go ahead and say this is V plus Ka times 16 because we are now assuming that n is 16. Okay, so we are computing, we're trying to determine whether -3 and 13 are congruent modulo 16. The question that we want to ask here is A congruent modulo 16 with B? That's the question. This is what we want to answer. Okay, so this is how -3 is going to be expressed, and this is how 13 is going to be expressed. Same V, but KB, but also the same 16, which is n over here. So now the question is, can you find an integer V that is non-negative, and it has to be up to 15, and also KAKB, which can be any integer, to satisfy these two equations? What do you think? KA should be okay. So this is this is math. This is algebra. How do you solve this algebra? You have two unknown and you have three unknowns and two equations. Okay. So how do you solve something like that? You can do a subtraction first, right? You can do a subtraction, then you eliminate the v. In other words, you do a subtraction of everything, the left hand side and also the right hand side. When you do the left hand side, let's just say that we do a 13 minus -3, it's a 16. On the right hand side, the v cancels out, so now you have kb minus ka, the whole thing times 16 is 16. So that's one way to solve it. But you can also just kind of intuitively look at this. Okay, so I'm just going to how we find a v and KAKB is not important. Okay, so I'm going to give you a potential solution. So let's just say that v is 13. Okay, so let's just say that for no particular reason, TAC says your v is 13. Can you solve Ka and Kb for me? If I tell you the v is 13, what would be Kb? This is 13. It'll be 0. Very good. And what would be Ka? Hmm? -1. That is correct. Okay. Are we okay so far with that math? -3 and 13 are congruent modulo 16, which means they are kind of the same thing. When you only have 4 bits, it can represent -3. It can also represent 13. Okay, are we okay so far? It is kind of odd, right? I mean, two things, two different values are quote unquote the same under this really kind of strange definition. But it's not strange at all. Okay, this is actually how integers are represented in a computer. They're always congruent modulo some powers of 2. Okay, the only question is what power of 2 we are using as n. Does that kind of give you an idea of how we're going to represent negative values? No? Okay, let's see. Okay, let's do it the other way around. Okay, so we'll use the whiteboard again, but this time we're going to do it the other way around. And this time I'm going to say, we're going to work it the other way around. We will say, I want to represent -5. Okay, n is the same, which is 16. This is A. I want to represent -5. Are we good so far? The question is, what is B? Okay, what do you think? Hmm? 11? Yep. So in this case, B is 11. So the way we figure that out is A is negative 5, but we are going to use negative 1 as Ka again. So this means negative 5 plus negative 1, which is our Ka, times 16. Nope, I take it back. We have to use the same V. Okay, I take it back. Excuse me. What is going to be V this time? V itself is 11. So now when we say 11 plus negative 1 times 16, that is negative 5. But what about B? B is going to be 11 times 0 times 16 plus 0 times 16. So that's just 11. So that means negative 5 and 11 are congruent modulo 16. Is that okay? So if this is kind of confusing because it's all symbolic and kind of mathematical, there's yet another way to look at this. Okay, the next way is going to be the easiest way to look at this. Have you guys learned about the number line? Number line, a line that is representing the numbers. Okay, so in this class we don't have a number line, we have a number circle. Okay, so we're going to draw a number circle. So what you do is draw a big old circle here. I have no idea how there can be holes on a whiteboard, but I'm not going to ask. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I'm drawing a wheel with 16 slots, okay? And I'm going to number these slots here. So I put a 0 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Are we good so far? Okay. So the number of slots on the number wheel is n. Okay. So now the question is, what are you going to do with this? Well, if I want to go from 0 to 1, I'm going to turn the dial or turn the needle in a clockwise fashion by one slot, right? So this is how we do addition, is to turn it in a clockwise fashion. What do I do when I want to do a subtraction? Counterclockwise. Very good. So if I start with 7 and I say I want to figure out what is 7 minus 2, then I go like click, click, it is 5. Are we good so far? Are we good? Are you sure? What is 1 minus 2? Well, let's make it 1 minus 3. Here's 1, and I said minus 3, right? Tick, tick, tick. It is 14. Does that make sense to you? It makes sense to you because 14 and negative 2 are congruent modulo 16. Is that okay? So that means I can now fill this table with some really confusing numbers. Okay, 15 pairs up with negative 1, 13 pairs up with negative 3, 12 pairs up with negative 4, 11 pairs up with negative 5, 10 pairs up with negative 6, 9 pairs up with negative 7, finally, 8 pairs up with negative 8. And we stop here. We stop here because now we have the same number of slots that do not have a negative pair or a negative component, and as there are clicks or marks with a negative component. 8 and 8. Okay, so you're squinting a little bit. Let's do some counting. Okay, so for the non-negative ones, the ones that do not have a negative component, there are 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. There are 8 of them because 0 is not negative. Okay, so 0 to 7 are the non-negative values. How many negative values do we have? We also have eight of them. One, two, three, four, five, 6, 7, 8. So the pie is evenly divided between negative values versus non-negative values. Are we good so far? We don't say positive values because zero is simply non-negative. Are we good? We're good. All right. So then the next question is, this is great, but if I have a really big number, I want to convert into like the binary representation, what do I do? So let's just say that this is the wheel that I'm dealing with, and I want to ask you about the binary representation of a negative value. Let's see what you can come up with. All right. So we have tried -3. We have tried negative. What was the other one? I cannot even remember. Let's try something. I think it's what -5. Let's try -4. Okay. So I want to figure out if I were to represent -4, what binary representation do I use to represent -4 as a value? So we look at this and go like, well, since -4 shares the same slot on the wheel with 12, okay, so we first recognize that. Now remember, this is congruent modulo 16. It does not say equal to. It is simply meaning that if I have to keep going around and around on a number circle, it would end up at the same slot. That's all it's saying. Is that okay? It does not say that -4 and 12 are the same value. It simply means if I were to rotate in a wheel with only 16 slots, they would end up on the same slot. That's all I'm saying. All right. But in terms of representation, they would share the same representation in base 2. So we'll check out the representation of 12. What is the binary representation of 12? 1100. Very good. Okay. Because it has 1 8, 1 4, no 2, no 1. That's why it is 1100. Okay. So that means, oh, okay, that's pretty easy. You give me any negative value, as long as it is from -8 to -15, I can quite easily figure out the binary representation. Does that make sense? Yes, go ahead. So -9 is not actually representable anymore because of because if we were to represent -9, or let me put it the other way. If we say that -9 is representable using only 4 bits, then we would have an uneven number of negative values versus non-negative values because we need that to be even. So the okay, so if you look at the signed value, which means both positive and negative, it would be from negative w, oops, -2, sorry. So it's going to be -2 to the power of w minus 1 to positive w to the, oops, I put w in the wrong place, 2 to the power of w minus 1, the whole thing minus 1. So this is the whole range of signed value on this number wheel. So let's check out whether that makes sense or not. Okay, w is what in this case? 4, very good. So 2 to the power of 3 is 8. So -8 is the lowest or the most negative value we can represent, given that we only have 4 bits. And it is. What is the most positive value? It is 2 to the power of 3, the whole thing minus 1. So it's 8 minus 1, which is 7, which is also the last non-negative value on this wheel. Is that okay? All right. So the biggest question that I have to answer is if I make W, let's say 16, okay, and I say, well, let's take a look at negative 2000. What is the binary representation of negative 2000 when W is 16? Is this approach going to work? You just draw out the entire number wheel and then figure out which part, which slot has negative 2000, and then look at the non-negative value also landing on that same spot, and then do the base conversion. Would that work? Well, it would work if you have, I'm gonna guess, like 2 or 3 days to do this, because how many slots would be on that wheel? Okay, so let's work this out. W is 16, which doesn't look too horrible. I mean, it's only 16. How many slots would be on that wheel? It'll be 2 to the power of 16. And what is 2 to the power of 16? 65,536 to be exact. Okay? So you have to draw a gigantic wheel with and then put 65,536 slots on that wheel. And then you start with a 0, right? And then you move counterclockwise by 2,000 slots. And don't forget that you have to label every single slot just so that you can figure out what number is corresponding to negative 2,000, and then you do a base conversion. Yes. Say that one more time, please. Um, okay, that's a good question. Typically, I don't get to that question until a little bit later, but since you're asking the question, I will answer the question with another question. Why do you care? Hmm? Curiosity. What if I tell you the computer doesn't care, and neither should you? Okay, let me say that in one more time. Okay, so when you look at 1100, for example, okay, you say, hey, the thing corresponding to 1100 can be a -4, but it can also be a 12. And my answer to that question of which one it is why do you care? And you should not care because 110 can also be representing 4 pixels on the screen. One pixel that is lit up, another pixel that's lit up, a pixel that is not lit up, and another pixel that is not lit up in the good old monochrome monitors. Okay? You don't know what it means until you use it. So until you have to do something with the bit pattern of 1100, it has no intrinsic value associated with it. It really is just literally 1100. But what does it mean? It can mean 4 integers, okay? One integer is 1, one integer is 1, one integer is 0, one integer is 0. It can be a portion of a larger integer, right? So we cannot answer that question until you use it to do something. Okay, so that's a very good question, but the answer is it does not have an intrinsic value associated with it. Until you do it, even addition and subtraction do not care. I can illustrate later on when we talk about comparison. The way we perform addition and subtraction, it will work regardless of whether 1100 is representing 12 or -4. It's going to work. And that's the beauty of this particular way of representing negative values. But until you add or subtract or try to display, use the 4 bits to display on the screen, we don't know what it is. So we don't say whether it's -4 or 12 or 4 pixels or two 2-bit numbers or a quarter of a 16-bit number. We simply do not know what it is. Yes. Okay, so can you repeat that question one more time? Uh-huh. It will work up to a certain point. Okay, so It'll it'll work to a certain point. Let's try that. Okay, so I still have to kind of keep track of where this class needs to be in order to deal with the lab tonight. But that's a good question. We'll kind of take a look. Can I erase the left hand side of the circle? I want the circle to stay there. Okay, so we'll go ahead and erase this side. All right. So do you want to do a addition or subtraction? You want addition of two negative values. Okay, all right, we can do that. And the negative one is, oh, that's not a part of the circle, so I can check that out too. So let's just say that we want to add -2 and -3. Are we good? It will work. It will work. Strangely, it's gonna work. Okay, so let's do this. Okay, what is -2 as a 4-bit number? Okay, -2, according to this table or not table, according to the circle, is 14. So -2 is represented by 1, 1, 0, 0, 14. Oh, you're right. Okay, I got it. So 14 is 1, 1, 1, 0 in base 2. And then the other one is -3, right? So we say -3, and -3 is 13, which is 1101, okay? Because it is 1, 1, that's 12, plus 1 is 13. So now we want to add these two. Is that okay? Okay, this is actually a really good practice of binary addition or just multi-digit addition. But in this case, it's base 2. This is x, this is y, this is q. Since it's base 2, the Q row is the exclusive OR between the X and the Y. Exclusive OR means if they're both zeros, the result is a 0. If they're both ones, the result is a 1. It's also a 0. If they're different, then the result is a 1. Okay, that's how we define the R function when we talk about the binary addition and also binary subtraction. So that means this is a 1 here, is a 1 here, is a 0 here, is a 0 here. Now we work with a K, okay? This is going to be a 0. We assume that is a 0. Okay, this is addition. 0 plus 1 does not have a carry. 1 plus 0 does not have a carry. So together, there's no carry over here. 1 plus 0 does not have a carry. 1 plus 0 does not have a carry. So we don't have a carry over here. 1 plus 1 has a carry. Stick a 1 here. We're done. 1 plus 1 also has a carry. Stick a 1 over here. And then this is the sum row, which is the R of the Q and the K, which is also exclusive OR. Okay, so this is a 1, this is a 1, that's a 0, this is a 1. Okay, so if you're not sure how I came up with the individual digits on the rows Q, K, and S, that means you need to go back and study. Okay, because that's something that we have talked about already when we talked about binary addition, which was 2 classes ago. The previous class was binary subtraction, and the one before that was binary addition. Okay. Now, if you say I can't do it as quickly, but I know how to do it, that's okay. Okay, you a little bit more practice will be helpful, okay? Because you really kind of want to be able to do this a little bit quicker. But if you know how to do it, you just cannot do it as quickly. It's okay. But not knowing how to do this or where in the notes we talk about it, that is concerning. Okay, this is only week 3. Okay, and this is the pace of this class for the next 13 weeks. This is the way it's going to be for the rest of this semester. Okay, it is super important to clear all the concepts of a previous class before moving on to the next class. Okay, but getting back to what we needed to do, what is 1011 as a base 10 number? Okay, hmm? It's 11, okay, but what negative value corresponds to 11? -5, okay. So if I add -2 and -3, should I get -5? It works out. Okay, so that's why this is a good way to represent negative value because the way we perform addition still works. Okay, and you can even mix and match positive and negative numbers. It will still work. If you want to say what is 2 plus -4? It's going to work out. Okay, it will figure out it's -2. All right, so are we kind of okay with this part? Okay, all right. So the next question is, okay, who's going to use a 4-bit number? And by the way, how do we call a 4-bit number? A 1-bit number is called 1 bit, BIT. And does anyone know why we call a binary digit a bit? BIT, binary digit. The B comes from here, the IT comes from here. That's why a binary digit is called a bit. Okay? And I'm not kidding. You can look it up. Okay? This is all documented in Wikipedia and whatnot. Okay. So what about a byte? Okay? A byte has 8 bits. So what do you call 4 bits? You guys you need some imagination here. It's called a nibble. And you would think that this is tech pulling your chain, but the answer is no. This is actually technical. Okay? 4 bits is actually called a nibble. I think they stop at a byte. I think they stop at a byte. Typically, in the good old days, a word means 16-bit, and then after that, they don't bother with actual names. All right. But anyway, um, do we even have a type in C++, that restricts an integer to only 4 bits? We don't. What about 8 bits, a byte? Which C++ type corresponds to an 8-bit integer? A char, that is correct. Okay. An int is anyone's guess. Okay. It can be 16-bit, can be 32, can be 64, depends on the compiler. Okay. So there's no telling when you use an int. So you can now say that, oh, okay, so a nibble is practically useless, okay, because no one is going to use a nibble as a type. So even an int, even the smallest int is 16-bit, okay? So an int, even the smallest one or the narrowest one is already 16-bit. So that means it is not practical to draw a circle with 65,536 slots, and then mark every single one, and then turn your wheel or turn the needle counterclockwise 2,000, and then figure out what positive integers is on that slot, and then convert the positive integer into binary number. That is just not going to work. Yep. Yes. Yep. So what do we do then? Well, the way we do it is by some really funky math. Okay, so we'll take a look at some funky math here. So we are skipping a little bit here. Okay, so now we're going to this portion. Okay, this is still good. This is still good. And now we are looking at some funky math, which is starting at this point here. Okay, so the mouse pointer is marking the focus right now. Okay, so I'm gonna say n is, in this case, n is for w being 16, n is 2 to the power of 16, which is 65,536. Is that okay? All right. But for the most part, you don't need to care about n, at least for this at this point. But we know that n is an integer. It is at least 2. Okay, that's all we need to know. So can I say this has to be true? Negative v is congruent modulo n with negative v plus n. Would that be, can we establish that congruency? What is the definition of congruent? If they're only off by, okay, look at the left-hand side. It's negative v, some kind of integer. The right-hand side is negative v plus n. So the question is it off by an integer multiple of n? It is, right? So if it is off by an integer multiple of n, those two values are congruent modulo n. Is that okay? All right. So now we shift our attention to the equality. Okay. So now we look at this equality over here. So we're looking at the left-hand side, which is negative v plus n. We look at the right-hand side, which is negative v plus open paren, n minus 1, close paren, plus 1, close paren. It's like, Tag, why are you rewriting something simple like n into something that is unnecessarily complicated, which is n minus 1, then we add 1 back to it? Well, I just need you to tell me whether they equal to each other or not. Okay, do they equal? They equal to each other. Okay, so now we have established this equality. So we move on to the next equality. So we now move on to this equality here, this one right here. So we now ask the question: are the left is the left hand side of this equality and the right hand side of this equality really the same? What do you think? Come on, you guys know your algebra, right? Negative v still exists in here, right? The positive n still exists in here, or the entire n minus 1 is still here. And then the plus 1, is pulled out of this, inner parentheses, and I just stick it outside. In other words, in terms of algebra, the equality should be fairly easy to establish. Are we still good? All right. So, but there's something special about n, because we know n is a power of 2. So you ask, so what is so special about n being a power of 2? It is not so much that n itself is interesting, it is n minus 1 being interesting. Okay, so then we say, okay, so what is so interesting? It is interesting because n itself is a power of 2, and then then we look at, you know um, a power of 2 minus 1. So the question is, what is so special about a power of 2 minus 1? So the key is, what does it look like as a binary number? Okay, so that's what we want to look at. All right, so I'm going to use the whiteboard to write out a few examples, and we'll start with something that we already know, which is 16, okay, or w equals 4. So when w equals 4, 2 to the power of w is 16, the whole thing minus 1 is 15. What is the binary representation of 15? We just talked about this earlier. It is 1, 1, 1, 1 in base 2, because it is 8 plus 4 plus 2 plus 1 in base 2. Okay, so we step up. Okay, 5 looks kind of boring. Let's look at 8. Okay, what is 2 to the power of 8 in this case? If you're in computer science, okay, hopefully in about a year or so, you can remember 2 to the power of 8, 2 to the power of 16, because those are really, really useful ones. 256, okay? 2 to the power of 8 is 256. 256 minus 1 is 255. Okay, and then you ask, what is the binary representation of 255? Okay, I think we have enough room. It has 1 of 128, 1 of 64, 1 of 32, 1 of 16, 1 of 8, 1 of 4, 1 of 2, and 1 of 1 in base 2. Are we seeing a pattern here? So a power of 2, the whole thing minus 1, would be a bunch of ones in binary, always. Now, I can prove this, but this is not a class about proofs, so I'm not going to use proof by induction to prove that. Okay, so if you took CISP 440 from me, you should be able to go like, oh, okay, I can do this myself. Use proof by induction to show that a power of 2 minus 1 would end up with just ones. Okay, and the number of ones would be W itself. Okay, but we are not going to prove it. So you go like, so how is that special, right? Well, the special thing about 1 1 1 1 1 1 1 1, or having a pattern that looks like that, and you're subtracting a number from it, that subtraction is also special. Okay, so we'll take a look at one particular one. Okay, so let's just take a look at 1111 as a base 2 number, and we'll subtract, let's say 3, well, let's subtract 4 from it, okay? So 4 is 0100. Okay, does it look like that I really need the rows Q, K, Q, T, and in order to get to D? Because it's impossible to have a borrow. Does that make sense to you? That it's not possible to have a borrow in this case? Because 1 minus 0 is a 1, and no matter what this is, there's no borrow. 1 minus 1 is a 0, but since this one is guaranteed a 0 also, it cannot end up with a borrow. So that means there's no borrow of 1. Okay, the entire T row is guaranteed zeros. So that means, oh, okay. So that means this is literally just 1 minus 0 is a 1, 1 minus 0 is a 1, 1 minus 1 is a 0, 1 minus 0 is also a 1. That's how we do it. Okay, and then you look at, okay, we'll name the rows again. This is X, this is Y, this is actually D. So you look at Y and D. Do they look structurally somewhat similar? Where the ones used to be, they became zeros. Where the zeros used to be, they became ones. So we're just flipping all the ones bitwise, and we're flipping the zeros bitwise, right? And guess what this operator is called? Okay, let me give you the actual question here. We'll call this the mystery operator. Okay, your circle, rectangle with a circle with a question mark. So this is x, this is y equals d. Okay, so what is the name of that operator? It's called bitwise not. Okay, bitwise negation. Have you guys learned bitwise negation in CISP 360? No, no. Okay, I guess nobody learned that. Okay, it's called bitwise not. Bitwise not is the tilde symbol. So the tilde symbol on the keyboard is bitwise not. All right. So you go like, okay, how does this connect to what we are talking about? Well, it connects to what we are talking about because when we get to this step here, this entire step is the bitwise not of the bit pattern of V. Let me say that one more time. I'm going to use the mouse pointer just in case someone is watching the video again. I'm talking about this portion here. This entire thing, okay, this expression is the bitwise not of the binary representation of V. Okay, so we just take the binary representation of V, do a bitwise not, that becomes that sub-expression, and then we just add one, and then guess what? We end up with a value. This whole thing as a value is congruent modulo 2 to the power of w of negative v. In other words, I just found the binary representation of negative v. Okay, so let's make sure that we make all the connections. Okay, the original objective is if I give you 2000, okay, and I say w is 16, or worse yet, 32 or something insane like that, okay, and I ask you what is the binary representation of negative 2000, you don't want to have to draw a gigantic circle with 65,000 or 4 billion, little ticks, okay? That's just not a good way to do it. So this is the way to do it, okay? It means what you need to do is to find out what is the binary representation of V, or 2000 in this case. That's not too hard, okay? Flip all the zeros and ones, okay? If you see a zero, flip it to a one. If you see a one, flip it to a zero, and then just add one to it. That becomes the binary representation of negative 2000. Is that okay? So we're going to formalize this a little bit, okay? And then we'll come back here to work out a few examples. So we skip a little bit to the definition, okay? So the definition here is one's complement is also the same thing as bitwise not, basically two things to represent the same operation. Bitwise not, which is taking each bit position and flip zeros and ones. That's called bitwise not, which is what the tilde symbol is representing. It's also known as one's complement, and that's what the C1 is representing. Okay, it's just a name. Two's complement, C2, is defined to be the one's complement of a bit pattern X, and just add one to it. That's all. Yes. One. Okay. If you ask what is the definition of complement, it depends on whether you're asking about one's. Okay, there are three possible possibilities here. Are you asking what is one's complement, how we compute that? Are we asking what is two's complement, how we compute it? Or are you asking what the word complement means in English? Okay, so the first one is this is the definition of one's complement. It is tilde x. It is the bitwise not of x, which is illustrated here. That is bitwise not. You start with Y, you end up with D, you flip all the bits. In this case, the ones complement of 0, 1, 0, 0 is 1, 0, 1, 1. But they are the ones complement is the reverse of itself or the inverse of itself. So that means the ones complement of 1, 0, 1, 1 is 0, 1, 0, 0 because you're flipping the zeros and ones, so it is reversible, which is also a concept called bijection, and it's also a concept that we talked about in CISP 440. That is how you take classes, okay? You make connections between the classes. The more connections you make between the classes, the easier it is to take the next class because you're no longer holding the knowledge piecemeal. They're all interconnection connected into a mesh. Because guess what? When you go to work, does your boss care? Is that a concept that they talk about in 310 or 440? Your boss does not care. Okay, the boss just need you to be able to do the job. Okay, which class it came from does not make a difference at all. Okay, the more you can make connections between your classes, the easier it is to take the next class or even the classes that you're taking. I used to take 3 computer science classes in one semester, but it felt like just a little bit more than one class because I can see the connections between the classes. All right. So did I answer your question? Yep. The second question is two's complement, which is By definition, the two's complement of x as a bit pattern is the one's complement of x plus 1. That's just plain addition. Okay, so we're going to work out that hairy example that I was talking about. What is the 16-bit representation of negative 2000? Okay, so we're going to work on that one. All right, so to work on that one, I'm going to use a text editor to do that. So where's my little text editor? Not this one. This one. Okay, there we go. Okay. All right. Get rid of that. All right. So we're looking at 2000. The first thing is I need to convert 2000 itself into a 16-bit number. Okay, a 16-digit binary number. Okay. Um, so we're gonna have to identify powers of two. So we'll start with 1024 and 512 for sure. 256 for sure. Actually, I'm just going to be super lazy and say this is 2048 minus 48. Okay. Um, because 2048 is a power of 2, so that makes it kind of easy. So now the question is, what do you think is the power of 2 that results in 2048? Hmm? Nope. Okay. What is the quickest way to do this? We are so doomed. All right, so the quickest way to do this is to think of 1000 in base 10 is approximately 1024, which is 2 to the power of 10. Yes, say again. Is D supposed to be? No. D is the difference between X and Y, so it's 15 minus 4. Yep. But because of the special property of X being all ones as a binary number, I don't have to worry about borrowing. So I can bypass the Q and the T rows. That's why. Okay. All right. So getting back to the quick tricks of figuring out how many bits we need to represent a particular value, or approximately. 1000 is approximately 2 to the power of 10. Okay. So if I know that fact, that 1000 is approximately 2 to the power of 10, that means 2000 is approximately 2 to the power of 11. Okay, and 2 to the power of 11 is exactly 2048. So 2000 would be that number. So I can now rewrite it, okay, as 2047 minus 47. Is that okay? Math is still working out. And guess what? 2047 is 2 to the power of 11 minus 1. So what is special about the binary representation of 2 to the power of something minus 1? It's all ones. Okay? In this case, how many ones are we talking about? 11 ones. Okay? 11 ones because 2 to the power 40, 2 to the 2048 is 2 to the power of 11. Okay, so we have 11 ones. Okay, so we just stash 11 ones here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, but we have to subtract 47 from it. So we look at 47 and then we ask, what is the best way to make 47? Well, 47 itself is not too bad. Okay, so this is 1, 2, 4, 8, 16, 32. Okay, so we're going to take out a 32, but we cannot take out another 16 because that would be too much. So we are going to take out all of these guys, I think. Yeah, because 47 minus 32 is what? Is 15. And what is special about 15? It is 2 to the power of 4 minus 1. So we just say, oh, okay. So that means these ones, which add up to exactly 15, they should all be zeros. There we go. So now we have the binary representation of 2000. Attack. This is how my friends call me. It's not just tech. It's hey tech. It has to be a little bit accent. So, hey tech. That's not a 16-bit number. Okay, this is an 11-bit number. I thought we were working with 16-bit number. Yeah, we're working with 16-bit numbers. So since there are only 11 of these, we just need 5 more zeros. 1, 2, 3, 4, 5. And here we go. We have a 16-bit number. We have a 16-bit number representing exactly 2000. And I did not use a calculator at all. So the key is, okay, this is something, it's a mentality thing, okay? So I cannot teach mentality. The mentality is, can I do this without a calculator? Can I do this without asking AI? Can I do this by hand? Okay. The idea of doing this by hand and not doing it using a calculator or asking AI is an exercise. Okay, it's a really small exercise. Okay, but nonetheless, it is asking your mind to think about base conversion. It's asking your mind to think about, okay, what does a digit mean in a number? Okay, so I think all of those are important. Okay, taking shortcuts is nice in the sense of it is more efficient to get a job done. The question is, are you here to quote unquote get a job done, or are you here to train your mind so that you can solve problems? Okay, so that really is the question. Okay, so now that we know this is X, okay, the next question is, what is the two's complement of this bit pattern? So I'll just be a little bit lazy here and do some copy and pasting. C2, the two's complement of this bit pattern, is C1 of the same bit pattern plus 1. Okay, so what is one's complement doing again? One's complement is also known as bitwise not, which does what? It flips all the zeros to ones and all the ones to zeros, okay, per digit, okay? So we look at each position and we go like, okay, this becomes 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 1, 0, 1, 1, 1, 1, okay? And just add 1 to it. They go like, this is like a really long addition. I need my calculator to do this. Nah, you don't need that. Because, because you can see how this position is going to have a carry, okay? It becomes a 0, has a carry, and then this position becomes a 0, which also ends up with a carry. And then the same thing happens here, the same thing happens here, but it stops here. That's the first 0. So 0 plus 1 is a 1. It doesn't have a carry of 1 to quote unquote infect the next one on the left hand side. So we know that's going to stop the whole thing. Okay. So that means I can now just say, oh, okay, the whole thing is just 1, 1, 1, 1, 1, 0, 0, 0, 0, 0, 1, 0, oops, 1, followed by all zeros. 1, 2, 3, 4. There we go. And this is the representation of negative 2000. Okay, so I'm going to say this is 2, and I'm going to use 0. I'm going to use this 6553536. I'm going to use that as a notation of congruent modulo 65,536. Okay, because they're not exactly equal, but it is congruent modulo that. Yep. Yes. Yep, so you guys need to do this kind of operation, but not with insane length like 16 bits. Say again? Well, it's in my notes anyway, and the recording will be available like 15 minutes into the lab. Yep, but you mean for binary subtraction? Um, okay, all right. So let's go back there. We have time to do it. Let me finish this, and then we'll go back to binary subtraction. Okay. So now the question is, well, this is what text is telling us, okay? He's telling us that 0, 0, 0, 0, 1, 1, 1, 1, 0, 1, 0, 0, 0, 0 is representing 2000, okay? I don't trust him, okay? He's known to make mistakes and he's known to trick people, according to ratemyprofessors.com. So what do you do? Okay. I'm not hearing the typical answer of drop the class. I guess 3 weeks into the semester, people are thinking, too late for that, right? Hmm? So how do you check this? Okay, we check this using a compiler, okay, or just GDB itself. So I'm doing something a little bit ahead of time, okay, which I think is going to be useful also, but I'm going to have to need it. I need it right away, which is base 2 to base 16 conversion. Okay, base 16 is also known as hexadecimal. Hexa is 6, deci is 10, so hexadeci is 16. Okay, it's base 16. So in base 16, this is a 0, this is a 7, this is a D, I think. Okay, and that's another 0. So now I can ask the computer and say, okay, if I give you a hexadecimal number, 07D0, what is the decimal representation of that? Okay, so we can do that. Okay, we can just write a tiny little program to do just that. Okay, so we'll borrow a prompt from here. Okay, I'm going to put it into the view and go to a folder here. Um, and just write a simple program. Okay, we'll say simple.c, and I will pound include standard integer.h. Okay, this is a really useful file to pound include in this class. Okay, int main, and then we have int. Uh, let's see, int 16 underscore t. Yep, there we go. And it's going to be uint, unsigned integer, and we'll call this x, and we'll say x equals to 0x. What was it again? 07D0, and then we'll also make x the same as the second value. What? Okay, I need to look at the bit pattern here. This one. So the way we convert this one is kind of the same deal. Chop it into chunks of 4, and then we use a table. There's a table to do the conversion. We'll talk about this later. Okay, so if you don't know what I'm doing, it's okay for now. So this is F830. Okay, so I'm going to type in F830 and return 0 at the end. You go like, how can this program possibly be useful? There's no there's no C in, there's no C out, there's no print whatsoever. How are we going to make use of this program? If you do not know how to do this, you really should learn how to do this, because this is a really, really important tool uh, to be successful in your other classes. So we use GDB. Okay, we're using a debugger. We put a breakpoint on line 5, run the program. It's now on line 5. So it is right before X is initialized. Okay, so we have the single step through line 5, and now X is initialized. So now I can print X. It is, guess what? 2000. Okay, if you go like, I don't trust that. Okay, can GDB, can you convert it back into hexadecimal so I can take a look at that? Yes. Isn't that cool? I think it is cool. All right, so single step one more time, and now your x is supposed to be negative 2000 because I just gave it the hexadecimal representation of the binary number that we just worked out, okay? So if I say print x right now, it should say negative 2000. Oops, what? No, because it's unsigned. Okay, I forgot to use the signed version, so I have to typecast it. Yeah, there we go. But typecasting is interesting too, okay? When you typecast something, you are really just asking about the congruent modulo equivalence of a bit pattern. Because in this case, 65,536 and negative 2000 are congruent modulo 65,536. It's just two ways of looking at the same bit pattern. Is that okay? All right. So let's go back and address the question of binary subtraction. Okay. Can I erase the circle? Okay. Because if people have not written down the circle right now, I don't have anything to say. Where's the pen? Right here. Okay. I hope you still remember how to do base 10 subtraction, multi-digit. So can I count on you to know how to do base 10 subtraction, multi-digit? Yes? Okay. I'll give you one example. Okay. What is 3 minus 6 in a multi-digit subtraction in base 10? This is base 10. The single digit difference is okay. Okay, let me okay, so you might want to write this down. Okay, this is the reasoning. Okay, this is the reasoning. Is 3 less than 6? That means we need to borrow. Okay, you write down a little borrow here. So when you borrow 10 and you had 3 to begin with, what do you have now? You have 13. Very good. 13 minus 6 is 7. That is correct. So you have a single digit difference of 7 and a borrow of 1. Okay. The difficulty of base 10 is that table, if you count 0 minus 0 all the way to 9 minus 9, is a 100 entry table because it's 10 by 10. So now we look at base 2. In base 2, you only got 4 choices. 0 minus 0 has a difference of 0 and a 0 for the borrow. 1 minus 0 has a single digit difference of 1 and a borrow of 0. Okay, so these two are pretty easy. 1 minus 1, kind of complicated. 1 minus 1 has a single digit of difference and also no borrow. Finally, we have the most complicated case, which is 0 minus 1 in base 2. So the first question is 0 less than 1? Yes, we need to borrow. We have a borrow of 1. The difference is a borrow of 1 from the next digit is a quantity of 2 because this is base 2. So now you have 2 plus 0, which is 2. 2 minus 1 is, yep, done. You only got 4 entries, of which only one is actually a little bit tricky because the other 3 are actually the same as the base 10 one. So does that answer your question? Minus what? Like this? Okay, all right. All right, so there are 2 ways to do this. We can do this. Okay, I don't want to quote the politician. But it's the same way. It really is the same way. Okay, so if you don't care about the middle rows, we just look up these four things. 1 minus 0 is a 1. There's no with a borrow of 0. 1 minus 1 is a 0. 0 minus this 0 is also a 0 with a borrow of 0 here. 1 minus 0 is a 1. 1 minus that 0 over here is still just a 1 with no borrow, with a borrow of 0 to the next digit. 0 minus 1 has a borrow of 1, but then you have a 1. 1 minus this 0 is a 1. So it's the same structure as a base 10 multi-digit subtraction. The only rule that is changed is this one. When we look at this in base 10, 0 minus 1 has a single digit difference of 9 with a borrow of 1. But in base 2, it has a single digit difference of 1, but still with a borrow of 1. That's the only difference. Everything else that you know about base 10 multi-digit subtraction still works in base 2 subtraction. Hmm. All right, perfect timing. So now we are ready for the lab, but you should not leave yet because you need an access code to the lab. That is two's complement. There we go. And I think I set up all the time and stuff like that already. You just need to write down the access code. The access code is, surprisingly, negative. And I think there are only 8 questions in this one, so, it shouldn't take. All right, I'll see you over in the lab, and I'll upload the notes for the